All right, so I'd just like to take this last video to sort of highlight some of the applicability of Taylor polynomials. Because if you recall, Taylor polynomials are essentially an approximation of a Taylor series, right? They're truncated at a particular term. And while sort of approximation is the word that comes out mathematically, scientifically, the word that probably is more so applicable would be prediction. And I tell you what, let me bring in this last example from the previous video that was talking about when we were looking at the square root of x. Our entire bit of analysis was centered only around the point x equals 9. And what were we able to do with this, though? We were able to predict what would happen at x equals 10. So yes, while mathematically we say, let's approximate this thing, if this was a scientific situation, we know what's happening at time 9, and now we are predicting what's happening at time 10. So there's actually predictive power in your Taylor polynomials. And to sort of like emphasize that, or maybe not emphasize, but to provide some justification that this may be the case, consider this. So here's a general formula for a degree 2 Taylor polynomial centered at x equals a, right? You got a constant that's your constant coefficient, then your degree 1 coefficient times a degree 1 polynomial, degree 2 coefficient times degree 2 polynomial. But of course, since it's a Taylor polynomial, we know what the form of these constants take. So that degree 0 constant is just f, the 0th derivative evaluated at a, technically divided by 0 factorial, but 0 factorial is 1. This one's going to be the first derivative evaluated at a divided by 1 factorial, second derivative evaluated at a divided by 2 factorial, right? Because in general, the nth coefficient of your Taylor polynomial is going to be the nth derivative evaluated at a divided by n factorial. That's Taylor's theorem, right? Now, what I'd like to do is to take this and make a couple specific alterations. So to this specific situation, right, to the situation that we see here now in the blue brackets, I would like to make two specific alterations. One, I would like to center our analysis at x equals 0. And two, I would like us to assume that our function f is a position function. So here, the position, right, because our function f is the position function, is going to be approximately equal to f of 0 plus f prime of 0 divided by 1 factorial times x. Note, here we're letting a equal 0, right, because we're centering our logic at 0. And just as well, x minus a becomes x minus 0, which is just x. Here we have f double prime at 0 over 2 factorial times x squared. So here we are at the degree 2 Taylor polynomial approximation of a position function centered at x equals 0. Right, so moving forward, what I'd like to do is shift this for a second, because really x, when you're talking about a position function, is probably the wrong letter here, right? We probably should be looking at this in terms of time. So I'm going to take x and put it in as t, because frequently when we talk about a position function at a given time, where is an object? So probably more appropriate to use t. And in fact, now down here in the second line, I've started to use t. But moreover, think about what this f of 0 is. That's the position now at time 0. Frequently referred to that as like initial position. This is the derivative of the position at time 0. So that's like the initial value of the velocity, right? Because velocity is the first derivative of the position function. And here now we have the initial acceleration, because the acceleration is the second derivative of the position function. And if you sort of rewrite this in different terms, frequently, at least in one-dimensional cases, we refer to the position as some position along the x-axis. X equals x naught plus v naught, that's velocity initial, times time plus 1/2 acceleration times time squared. I don't know if you've ever taken a physics class, but this is a classic formula that is memorized in a physics class. And this formula is now, you can see, nothing more than a degree 2 Taylor approximation of a position function. That's all it is. And in fact, you could tack on other terms if you wanted to. You could tack on, right, if you were interested in more precision, you could tack on a 1 over 3 factorial times whatever the acceleration's derivative is, which I think is technically called jerk, times t cubed, and you could play this game out as far as you wanted to, which is kind of interesting. Now, frequently, I should say, in a physics class, you don't just have approximation, you have equality, and the reason for this is because we assume that the second derivative of the position, we assume that the acceleration is constant. Because if the acceleration is constant, then all higher derivatives are going to be 0. And so then you will have no non-zero higher terms in your Taylor series for your position function, should your acceleration be constant, which is frequently where we use this formula, because this formula is often applied whenever you're under the influence of gravity, which is a constant accelerating force. Okay, so then you say, okay, so what? Maybe you have or haven't taken a physics class. Let's at least see how the predictive power of Taylor polynomials can be utilized. So, example: assume a dolphin is swimming away from a reef. At noon, the dolphin is 1 mile from the reef, swimming at 2 miles per hour with an acceleration of 0.3 miles per hour squared and a jerk of 0.02 miles per hour cubed. Remember, jerk is just the derivative of acceleration in effect. Estimate how far the dolphin is from the reef at 1 p.m. Because you see, we know all of this information about the dolphin at noon. It's swimming away from the reef. It's already 1 mile away from the reef. It's swimming at 2 miles per hour, but it's not just swimming at 2 miles per hour, right? It's accelerating. Moreover, its acceleration is changing speed. These are all factors that should be considered if we're going to be making a proper estimation based on the data. Well, we could take all of this data and we could encode it into a Taylor polynomial. So the function should be approximately equal to its initial value plus its initial derivative value divided by 1 factorial times x plus its initial second derivative value divided by 2 factorial x squared, initial third derivative value divided by 3 factorial x cubed. Here, assume x is the hours after noon. So note, this is a Taylor polynomial centered at 0, because if we just take noon to be time equals 0, then that works out really nicely. And f of x, assume that's the distance from the reef, right? So initially, the distance from the reef is 1. So in fact, if you plug in a 1 here, which is the initial distance from the reef, and then 0 out all of the other values, you would get that f of 0 is equal to 1, which is precisely the case, right? At noon, the dolphin is 1 mile away from the reef. Now, we don't want to know what's going on at noon because we already know what's going on at noon. The question is, where's this dolphin going to be at 1 p.m.? Well, we can use our Taylor approximation and the information that we subsequently have about the speed of the dolphin and the acceleration and the jerk to produce ourselves an approximate estimation, a prediction, if you will, for the position of the dolphin at 1 p.m. And so you just take the function that comes out, this degree 3 Taylor polynomial, and you plug in 1, because that's going to give you the estimate that the data that we have would provide 1 hour after noon, which is exactly at 1 p.m. And when you run the numbers, you get 3.153 miles, which kind of makes sense, right? Because the dolphin was 1 mile away and was swimming at 2 miles per hour. So just off of that data alone, you would expect the dolphin to be 3 miles away. However, the dolphin was also speeding up. There was some amount of acceleration, and even that acceleration was accelerating, that acceleration was at least speeding up. In the sense that the jerk had some value as well. So it kind of makes sense that the dolphin would be further than 3 miles away, because its speed at noon alone would dictate that it was 3 miles away, and it was speeding up even over time as well, which is accounted for in this prediction. I mean, hell, now we know where approximately where the dolphin's going to be at 1 p.m. What about at 2 p.m.? Well, you could play the same game. If x is number of hours after noon, just take this same polynomial and evaluate it at 2, and as it turns out, you get 5.627 miles, which also kind of makes sense that the dolphin's making more headway, whereas between noon and 1, the dolphin is assumed to have only gone 2.15 miles. From 1 to 2 now, the dolphin's gone like almost 2.5 miles. And why would that be? Well, because the dolphin's accelerating, right? It's speeding up. So give the dolphin more time to speed up. It's going to be going even faster. The jerk is also affecting the acceleration, which is making the dolphin speed up just as well. So here's an approximation of where the dolphin's going to be at 2 o'clock. Now, I should say this. If this approximation is going to hold true, then we would be acting under the assumption that this dolphin's acceleration is continuing for 2 hours straight. And this jerk, the change in the acceleration, is continuing for 2 hours straight, right? Which might even already be a hasty assumption. If we were asked to figure out where this dolphin's supposed to be at 8 p.m., it's probably super hasty to say that we could use the information that we had at noon that to predict the dolphin's position at 8 p.m. That seems a little bit out of reach for our data, right? Because our data and our analysis was based at noon. Are we going to assume that the dolphin was speeding up at this rate of acceleration for 7 hours? Does that make sense? That might be a little bit hasty. So if we wanted to know where the dolphin was at 8 p.m., if we could just get our hands on data from like 7 p.m., then yeah, maybe we could make a prediction. But at the very least, while yes, the Taylor polynomials and their predictive power is somewhat limited in their scope, there is the ability to get a really nice estimate for particular values off of a function, or in this case, the prediction for where our dolphin is going to be using our Taylor polynomial. So I just wanted to go through this video for, if nothing else, like mathematical culture, or better yet, even scientific culture, so that you can realize how the mathematics that we've discussed related to Taylor polynomials can actually reflect back into the sciences and give you quite a powerful tool to utilize in terms of predictive ability.